Welcome to Quick Soil Mechanics Lessons with Brian. Liquefaction simply explained in 12 acts. Act 6, Stress Paths and Static or Flow Liquefaction. Let's start off with our axes. Normal stress on the horizontal, shear stress on the vertical. We've got two different failure envelopes, total and effective stress. We have a point representing our consolidation point, and on the lower left, we've got a triaxial test sample designating the conventions there, sigma 1 being vertical, sigma 3 and 2 horizontal. So we've consolidated a point out here, isotropic consolidation. So sigma 1 equals sigma 3, so it's a point. And we start to grow that point. Here it is in total stress. And here it is in effective stress. And the difference between those two circles is the pore pressure. So we continue to shear this sample. And we have our total and effective stress circles. And the total stress you can see is growing up in a specific pattern. Sigma 3 is remaining constant, sigma 1 is increasing. However, the effective stress circle is just going wherever it wishes based on whatever is the pore pressure at that time. So we continue to shear until we hit failure. Here it is, failure on the total stress, failure on the effective stress, and we can put a point at the top of each one of those circles, connect it with a straight line at a slope of 1 to 1. For the effective stress, it's different. It doesn't go up any straight line. It goes wherever it wishes to based on the pore pressure that's developed during shearing. We can clean that up a little bit. And again, we can show that straight line is the total stress path. The red line is the effective stress path. Clean it up with those points because those points aren't really real. There's an infinite number of circles in between. So this is the MIT space. So it's at the top of the circles. That's the total stress path, effective stress path. Now there are some useful patterns that you can look at. So for the effective stress path, this is what normally consolidated clay looks like. We have other cases where we might have a compacted clay, always has a stress path like that. A lightly over-consolidated clay has a stress path like this. And if we put up a one-to-one line, we can see a curve like this, and that's a heavily over-consolidated clay. These are typical stress paths for clays. So let's talk about static or flow liquefaction. First of all, Peter Robertson prefers to call it flow liquefaction because it can happen under either static or non-static conditions. We'll talk about that a little bit later. So here on this page, we have a couple of facilities in Brazil that failed a few years ago. Upper left-hand side is Samarco. Upper right-hand side is Brumadinho. And below each of those is what they looked like after they failed. So they both catastrophically failed and flowed with classic flow liquefaction characteristics. These are some results of some static liquefaction or flow liquefaction events on tailings facilities. Left-hand side, this is Stava in Italy. Upper right-hand side is Samarco. Lower right-hand side is Mariesprate in South Africa. So what does that look like in the lab? So we've got our two different stress spaces. We've got stress strain space on the left and stress path space on the right-hand side. So this happens to be the MIT stress path space. So this is a characteristic failure curve for flow liquefaction. We can see we have at very small strains, we've got a peak and a very rapid drop off, so it's very brittle, drops down to pretty low strength. And stress path space, it looks like this. So it also hits a peak, drops down to a low minimum. So here's one of the dangers. A lot of people would say, well, let's use that large strain strength because that's the lowest it's going to be. But if you look on the right-hand side, the lowest strength actually corresponds to the friction angle. And so that would be unsafe to do. Instead, we take the top of that line, and that is designated as the yield surface, sometimes a collapse surface. Different people call it different things. But taking the top of that surface is far more realistic, but we'll see we don't always have to go through the top. So that's just the peak strength. Now, if we had a family of these, we would see that we've got the peaks are all the same in this case, so the yield surface is constant for all those samples. Getting back to our first chart, though, let's just move things over a little bit. So we've got some static shear, like might exist on the outside of a slope of that tailings dam, for example. So we can get to that ultimate strength in different ways. So on the left-hand side, we cut that peak straight off. Same thing on the right-hand side. We don't go through the peak. We'll get to how that can happen shortly, but we can also get there by having some dynamic loading or vibratory loading, earthquake, same thing on the right-hand side. So what do we call those? So left-hand side, we can see the peak. This is a curve that's static or a constant loading rate. The blue line is creep or also a constant Q. And what we mean by constant Q is a increasing pore pressure under drained conditions. So the more circles basically staying the same size but sliding off to the left. That's what the blue line represents on the right-hand side, is that more circle stays the same side, but it slides off to the left. That's what that stress path is telling us. And then on the red, we've got seismic or cyclic loading. So we can cause flow liquefaction in many different ways. Well, I think that's enough for today. If you missed the first 5 lessons, you can go back and find those on my YouTube channel. I think that's plenty. We don't want to overdo it, but thanks for attending, and we will see you next time.